Okay, so I'm picking us back up at example 2. I did take a moment to recalibrate the screen, so hopefully our notations will be a little bit easier to work with. Okay, so example 2, we're talking about graphing these natural base functions, these functions that include the letter E. If you'll cooperate with me. Okay, so two things we want to work with. These are going to be exponential functions like we dealt with in lesson 4.1 and 4.2. Thing we want to look for is the exponent. If the exponent is negative, it is a decay function. So you'll notice that as x increases and reaches infinity, the graph approaches y equals 0. The same ideas of having an h and a k apply. So if you see anything being added to the x value, that's going to shift our graph over left or right. And if we have anything being added to the entire function, like a k value, that's going to shift our graph up or down. So the same rules of exponential functions still apply. If our exponent is positive, then we are going to talk about a growth function. So again, as x approaches infinity, then our y value is also going to approach infinity. But as x approaches negative infinity, our y value is going to approach whatever the k value is. So in this case, -2. And you can tell here, the graph is counting by 2's. So here's -2, and as x goes along, it's getting closer and closer to -2, but never quite reaching it. Now, as far as how to graph these functions, well, of course, the easy way is plug it in your graphing calculator, hit enter, adjust the window as necessary. But for those of you that are good at building your tables, which many of you are, which is fantastic, always when in doubt, go back to your basics. All right, go ahead and make the same idea. Build your x and y table, plug in some values of x. This would represent what's going to happen to the exponent. And then, as I showed you before, you're going to hit Shift, E, and then whatever in the parentheses, plug in your exponent, and then close the parentheses, hit Enter, and it's going to give you some value. So, of course, if I have 0, oops, I meant 0 here, as my x value, well, e to the 0 power is 1. Anything raised to the 0 power is 1. So 1 times 4 is 4. So, again, some of these nice basic things work out. I told you before that e was equal to approximately 2.718, blah, blah, blah. So e to the first would be 2.71, but we're going to take negative half of that. So that gives us a value of 0.1 whatever, and then multiply by 4, and we end up with, actually that made us a decimal, apologize for that, spoke too quickly. But when we multiply by 4, it gives us the value somewhere around here, and then multiply it by 2 to get 1.47, because everything would even out then. As we plug in for example B, again, use our calculator for these functions. Go ahead and type in your x and y value for -1, 0, +1, +2, so on and so forth. Again, make adjustments for the fact that, all right, you have an h value of +2, and you have a k value of -2. So, taking your basic graph of e to the 2x, go ahead and adjust that to, actually, your h value is -2. You're going to shift it to the left 2 spots and shift it down 2 spots because of that k value. But again, when in doubt, use your graphing calculator. That's why I go there. All right, so let's take a moment. And we'll look at another multi-step problem, which again goes straight to using the calculator. Then I'll give you an example. So a population of bacteria can be modeled by the function P equals 70 times e to the 2200ths times t. All right, so here's our function here. Here's our function here. Okay, oops, I accidentally moved that down, but we'll be able to see over that. T is the time in hours. Graph the model and use the calculator, use the graph to estimate the population after 4 hours. Moved it down a little so it's kind of hard to see. So plug in this function into our calculator, hit graph, go ahead and adjust the window as necessary to be able to see our numbers, and then use the tracing feature to follow that curve until you get to x equals 4. And then whatever this value is, that's your t value. So we want to go ahead and round it to approximately how many, or how much bacteria after 4 hours. So sorry, x is your t value, y is your p value. So the population of bacteria is about 169. So kind of like people, you want to round up for these whole numbers. So the population of bacteria is about 169 after the 4 hours. Okay, so now, let's see if I can move that back up. There we go, much better. Moving on to our exercise. So here are 3 functions that I want you to graph, and then state the domain and range, just like we did with the exponential functions from lesson 4.1 and 4.2. And then take a look at example 3 again to estimate the population after 5 hours using this new population model. Hit pause, take as long as you need to suitably graph these functions, and then when you're ready, go ahead and hit play to move on to the next answer. Okay, so here are the 3 graphs. Here's the domain and range, and the answer to question 8. Again, circle any questions you have, and we'll go over them in class. Example 4. Talking about finance again, so exponential growth, it's always nice to have finance examples. Now we have a new formula. Notice that we are talking about when things compound continuously. That means as soon as interest is earned, it's earned again, it's earned again, it's earned again, going on and on and on. There's a formula we use for that where the account balance is equal to the principal times E raised to the RT. Principal amount, rate, R is equal to the interest rate, and T is equal to time in the number of years. And the interest is compounding continuously. So, plug in our values. $500 times E raised to, we got 3% here, so put that in decimal form. And our time, how many years? So we have 2 years. All right, plug that into your calculator. I always just use order of operations, so 500 times E, and then the shift, or you have to hit shift E to the X, and then plug it all in. Close parentheses, it goes pretty easily with the calculator. And your final answer is something approximately $530.92 in US money, rounded to 2 decimal places. So maybe you missed that on our exit ticket yesterday. So when you round to 2 decimal places. Don't round to the nearest dollar, round to the nearest penny. All right, so again, remember this formula here. We're going to be using that on our next example. Okay, so let's take a look at exercises for example 4. Read the question, pause as long as necessary to solve the 3 problems. 1 year, 3 years, and 5.5 years. When you're ready, hit play, and you will see the answers. Okay, so just quickly write on here what the answers were. So for 1 year, $2,081.62. For 2 years, $2,254.99. And for 5.5 years, $2,492.15. Again, if you have any questions, circle them. We'll talk about them in class. Now that's our last example. Remember that on Monday we'll have a quiz on lessons 4.1, 4.2, and 4.3. So we need to make the most use of our time in class tomorrow so that we can do well on our first quiz for semester 2. I'm going to be available for you all day long. Good luck studying.